What's up, guys? Look at two things this video: atom economy and percentage yield. Worth mentioning now, if you haven't looked at the reacting mass video, now's the time to check it out. Although if you're pretty confident with the reacting mass calculations, feel free to leave it. I'll leave the link in the top right corner. So atom economy. Essentially, the easiest way to look at these is to look at the equation. So here we've got mass of desired products divided by our total mass. And we generally have this as a percentage, so we times that by 100. And essentially, the higher this is, the better, as it will mean there is less waste. And there's various considerations there. Sometimes the waste is toxic, sometimes the waste is going to take up landfill, etc., etc. So in terms of making money, at high atom economy is going to be a very good thing. Percentage yield. We've got our mass of products, or our yield, divided by our theoretical yield. And again, we'll times that by 100 to turn that into a percentage. Now, generally speaking, our theoretical yield is going to be calculated within our reacting mass question. And we've sort of looked at how to do that here. And our end result is this 11 gram value. That's our theoretical mass in this case. And a question would give us an actual mass and we'd work things out. But worth us thinking about, why is our percentage yield not going to be 100%? There's a few different reasons. So reason one is we may have a reversible reaction. So at that point, the reaction will be incomplete. Reason two is we might have side reactions. So that's when we have a product that we don't expect to have necessarily. An incomplete combustion is a very good example of that. And sometimes we just have loss of product or reactants. And that can be through various things, such as when we transfer one substance from one container to another container. We may have some stuff left behind. So there, we sort of need to have this general idea as to what percentage yield is, and then use our knowledge of a particular reaction to work out exactly what's going on. So let's go through a couple of examples. So here, again, all of my examples here are going to be based on this set of questions that we looked at in our reacting mass video. So we're going to look at this question, the 16 grams of oxygen, and then for a question I want you guys to give a go, we're going to look at the one below it. So here, what if only 8 grams of CO2 is made? So like I said, in this question, we've already worked out that our theoretical mass is 11 grams. So here, to work out our percentage yields, we're going to do our actual yield, which was 8 grams, as it tells us, divided by our theoretical yield, which is 11 here, sorry. Times by 100 in order to convert that into a percentage. And there we get to 72.7%. Why might less be made than expected? So again, let's have a little look at the reaction. We've got methane plus oxygen makes carbon dioxide plus water. So straight away, I know that we've got a combustion reaction. So I think there's a good chance that we've got some incomplete combustion here as well. So there we might have some carbon produced, or we might have some carbon monoxide produced. So there, my big thing here is we could have incomplete combustion. So there we might have some carbon produced or some carbon monoxide produced instead. And again, we could talk about the others as well, but this is sort of the main bit where we've got a bit of insight into the equation. So atom economy with respect to CO2, again looking at that same equation. So here, let's grab this equation. And again, we're looking at our products, right? So now let's just work out the MR of both of those things. So the MR for CO2, we've got one lot of carbon, which is 12 if you look at the periodic table, plus 2 lots of 16 for oxygen, getting us to 44. MR of H2O, we've got 2 lots of 1 for hydrogen, plus 1 lot of 16 for oxygen, getting us to 18. So now when I do my atom economy, my desired product is just the carbon dioxide, so 44, divided by my total mass of products. So there we have the 44, and we've also got 2 lots of the 18. So this is the one case where we are going to look at the big numbers when we're talking about our MRs. So there we've got 44 plus 2 lots of 18, getting us to 44 over 80, but we need to times that by 100, of course, getting us to 55%. And last bit, why is a high atom economy preferable? Very simply, less waste products. Perfect. So, questions I want you to give a go are in relation to this, to the aluminium here. Again, let's take this. And here are theoretical yield of aluminium. Is there the 1001.18 grams. Give that a go. Now we'll look at the answers to the titration question at the end of last video. So here, titration. Student dissolves an unknown mass of sodium hydroxide in water to make 200 centimetres cubed of an aqueous solution. A 25 centimetre cube sample of this sodium hydroxide solution is placed in a conical flask. So I know that at some point I'm going to have to work out how many moles are in the 25, and then use that to work out how many moles are in the 200. So I'm going to make a little note to myself that at some point I'm going to have to times my value by 8. Titrated 0.150 moles of sulfuric acid. The equation for this reaction is below, happy days. Then we've got our titration. So here I'm looking for concordant results. I ignore the rough. I'm only looking at 1, 2, 3. I've got 19.60. 19.85 is 0.25 away. That's too far away. the 19.55 is within 0.1. So these are our concordant results. So calculate the mass of sodium hydroxide used to make the original solution. So I've got CNV, I've got mass, Mr. mole. These are our little triangles that we need to use. First thing, let's work out what our volume is here. So we've got 19.60 plus 19.55 over 2 gets us to 19.575. Now we can start putting everything in our table. So we've got 2NaOH plus, and we've got H2SO4, CNV. We've got the volume of sodium hydroxide is 25 over 1,000. H2SO4 we've just worked out, 19.575 over 1,000. And our concentration of sulfuric acid was 0.150. Now I can start working. So CNV, to work out my moles of sulfuric acid, I'm going to do concentration times volume, which gets us to 2.936 times 10 to the minus 3. Now I use my molar ratio to work out how many NaOH I have, so I'm going to have to times this value by 2, which gets us to 5.8725 times 10 to the minus 3. So that's our moles in 25 centimetres cubed. I need to know the moles in 200 centimetres cubed. So again, that's why I've got this signal, times by 8. So there I get to 0.04698. So that's the moles of sodium hydroxide that I had in this 200 centimetres cubed aqueous solution. Now I've got enough information to work out my MR, and that means I'm going to be able to work out my mass in the original solution. So MR of NaOH, if we look at our periodic table, we've got one lot of 23 for sodium, plus one lot of 16 for oxygen, plus one lot of 1 for hydrogen, getting us to 40. And now, to work out my mass, I'm going to do MR times mole, which is MR times our value here, getting us to 1.8792 grams. Perfect. Couple of other bits. B. The student use a funnel to fill the burette with sulfuric acid before starting the titration. So imagine here, we're doing our titration, we've taken our initial reading, but there's a funnel still in. There could still be little bits of our solution there. So after we've taken our initial reading, we could be getting drops in. So what that's going to mean is that our reading is lower than it should be. So here, additional drops. Could have entered the burettes. C. State one advantage of using a conical flask rather than a beaker for the titration. Very simply, if we think about a beaker, if we're swirling this or if there's drops coming in, splashing is going to be very easy. Whereas with a conical flask, we've got a much more narrow top, which means splashing out or swirling is going to be less risky. So we've got less chance of losing solution. Great. I hope that's helpful. In the meantime, happy revising, guys.